Last thing we're going to talk about in chapter 8, section 6, is the difference in absolute convergence and conditional convergence of a series. We're talking about any series. Doesn't have to just be an alternating series now. So we could have a series of positive terms. We could have a series of terms that have different signs. Certainly you could have an alternating series. But we say that the series a sub k converges absolutely if the series of the absolute value of the terms converges. Okay, otherwise, if the series of absolute values doesn't converge, but the series a sub k does converge, then we say the series converges conditionally. So there's a theorem that says if the series of absolute value of a sub k converges, okay, so if the series is absolutely convergent, then we can conclude that the series a sub k also converges. So absolute convergence implies convergence. So if you show to begin with that you've got absolute convergence, you don't have to do any more work to say that the original series converges. The second part of that theorem says if the series a sub k, original series a sub k, diverges, then the series of the absolute value a sub k will also diverge. Okay, now it's important to kind of think about some points here. Point number one, thinking specifically about whether or not a series is absolutely convergent is only important for series of mixed signs, some positive and negative terms. If you have a series of positive terms, then the absolute value doesn't change it. So showing a series of positive terms converges, in effect, shows that it's absolutely convergent. Okay, that's worth kind of making note of. If a series of positive terms converges, it converges absolutely. If we're going to take a look at a series and test for absolute convergence, start by looking at the series of absolute values. Because if you can show that converges, then the series of regular a sub k's is also going to converge. You have an absolutely convergent series. Alright, so we're going to start with this. I don't want to say it that way. We're going to use that series to test for absolute convergence. So we're gonna make our series a series of positive terms. So we're going to be thinking about the convergence tests from section 8.4 and 8.5. The integral test, the ratio test, the root test, the comparison test, the limit comparison tests. Because we're taking absolute value, we're going to basically create a series of positive terms, even if we don't have one to start with. And the test for convergence of series of partial sums came from section 8.4 and 8.5. So you may need to go back and refresh yourself a little bit on those. So let's jump in with an example. I have a series, if k starts at 1 and goes to infinity, of negative 1/3 to the k power. I'm going to consider the absolute value of negative 1/3 to the k power. Because what I want to do here, I kind of forgot to tell you what I was doing, we want to determine if this series converges absolutely or converges conditionally. It's going to be a series that converges. I'll go ahead and tell you that. But does it converge absolutely or conditionally? So we're going to test for absolute convergence. I can kind of clean that notation up a little bit. Basically, the absolute value just removes the negative, and we're looking at the series 1/3 to the k power. Now you've got to think about how you would test that series for convergence. And I think this one is going to be one where the ratio test is going to work well. So I'm going to look at 1/3 to the k plus 1 power divided by 1/3 to the k, and consider the limit as k approaches infinity. I will confess to working this before I jumped in to start making this recording, so I know this is the comparison, the test for convergence that's going to work for me. Clean it up a little bit. You're looking at 3 to the k divided by 3 to the k plus 1. If you invert and multiply, which you can reduce to 1/3, and then the limit as k approaches infinity of 1/3 is 1/3. Okay, now, so in the ratio test, this is our value r. So we found that r is 1/3, and the rule is if r is between 0 and 1, then our series converges. So the series, that series converges by the ratio test. So we can conclude then that the series that we started with, the original series of negative 1/3 to the k power, converges absolutely. Another example, we have a series from 1 to infinity of negative 1 to the k power times k squared divided by the square root of k to the 6th plus 1. So we're going to consider the series of k squared over the square root of k to the 6th plus 1 and try to determine if that series is going to converge. Now, if I'm thinking about what's happening as k gets pretty big, then this expression is going to be getting more and more like k squared over the square root of k to the 6th. In other words, that plus 1 in that denominator really doesn't make a whole lot of difference when k is getting big. That's similar to 1 over k, or excuse me, k squared over square root of k to the sixth is 1 over k. And I know that the series, if k starts at 1 and goes to infinity, of 1 over k diverges. I know it diverges because it's the harmonic series, a non-alternating harmonic series, so that diverges. So I've got a series that I know diverges. I'm going to try the limit comparison test. And I'm going to take a limit of k squared over square root k to the sixth plus 1 over 1 over k. And we're working the limit as k approaches infinity. Okay, and in this situation, this limit for some reason is p. And the deal is, if p is between 0 and infinity, then we're going to know that our series we're looking at does the same thing that 1 over k does. So, working on this limit, we end up with k cubed over the square root of k to the sixth plus 1. That limit eventually, another couple of steps, or maybe you can see it right there, that limit is going to be approaching 1, and 1 is somewhere in between 0 and infinity. So the series from 1 to infinity of k squared over the square root of k to the sixth plus 1 also diverges. So what we've done at this point is we've ruled out absolute convergence. So the original series does not absolutely converge. We can still check for conditional convergence. So going back to the original series, it's an alternating series. So I'm going to apply the alternating series to this. I'm going to think about the limit as k approaches infinity of k squared over the square root k to the sixth plus 1. That limit is actually going to 0. So the next thing I need to think about is the function x squared over square root x to the sixth plus 1, if you think about that. And honestly, I'm not really terribly worried about how you decide this is non-increasing or not. But this function does decrease. In fact, I think we could probably, let's just see. Now, I've not done this, so it may not work. But if I graph that function, x squared over hello, wake up, there we go, over the square root of x raised to the sixth power plus 1. And if I just graph that on a standard viewing window, I'm thinking about, it's really hard to tell on that viewing window. So we want to look, it was very, very close to the y-axis, so let me go -1 to +1 on the y min and max. Okay, looking out a little bit further, make your x max something bigger. you could go really big, like, 100 or 210 for some odd reason. Okay, there's certainly some evidence there that the terms of this series are going to be decreasing terms or non-increasing terms. So the series -1 to the k squared over square root k to the 6th plus 1 is conditionally convergent, or converges conditionally is a better way of saying that.